Good. That's December 10th, 2025, the last day of class meeting before the final exam. And we are covering waves. The easiest, the simplest type of wave that that you can visualize is the wave in a string. You get a string or a rope and you oscillate back and forth. Okay, this oscillatory motion can be like a simple harmonic motion. Okay, and a full oscillation has a given period, occurs within a given period. The interval of time for a full oscillation, we call it the period. Not just the period of the oscillation, but also the period of the wave that you are generating. As you move back and forth, what's going to happen? You're going to generate a wave that's going to propagate from the source, from the point of the source. Here you go. At time t equal to 0. The wave is right in here. A little bit later, it moves a little bit, right? Another second later, another second later, another second later, and so on. This is a simulation that I prepared here in Excel. Okay, it's possible to do those things. It's possible even to animate, but I decided not to animate it. I'm doing just the animation in the manual sense, right? But Excel allows you to do a full animation of something like I'm doing right now. And here you go. Let's go until up to 20 seconds. And then what I'm gonna do, I'm gonna rewind my movie, right? Oops. Here you go. And I'm gonna play this movie again. Look here, the wave propagating from the left to the right. Just by moving the end of our string up and down. Okay? That's what we observe when we do something. And we're talking about a very long string. I'm not talking about a string of with the two ends fixed, right? But the a string with both ends loose. Okay, so we can waterways. Waterways is another example of a wave. Everybody has been at the ocean, have seen water waves in the ocean, right? And it is energy that's propagating along the medium that is the wave. In this case here of the string, right? The string is the medium along which the wave propagates. The immaterial wave, let's put it this way, immaterial wave propagates. The string is the medium. And here in this case, not the string, but the water is the medium along which the immaterial wave, the water wave, right? The immaterial water wave propagates. Sound. How do sound propagates in a medium. The medium, let's say, of propagation of sound can be the air, a gas, a solid, etc. Okay, and that I mentioned here as well. In general, okay, in general, a wave requires a medium to propagate. Okay, until recently, until the beginning of the 20th century, not the beginning of the 20th century, until the end, not beginning of the 20th, until the end of the 19th century, comma, end of the 19th century and beginnings, right? And beginnings of the 20th century, scientists thought that no wave, that no wave could propagate in the vacuum. That's what we thought at the time. Okay. We thought that a wave required a physical medium to propagate, but we were wrong. We were wrong. It's very important to keep that in mind, okay? Because that shows how science evolves. And let's see, Edith is raising her hand, right? Yeah, Edith, do you want to ask a question?
Yes, Professor, good morning.
Uh-huh.
I had a question about the Wiley homework. I was
Yeah.
wondering, is that due on the 15th?
Yes, the 15th of December. That's right.
Okay, perfect. Thank you.
Is there a problem there? Or everything sounds no problem
Yeah,
there,
I,
right?
I was just, yeah, no problem.
Okay, thank you.
Thank you.
Okay. So here you go. Let me give you more examples of propagation of wave propagation in a medium, right? And then I'm gonna give you an example that we can have a propagation of a wave in vacuum. And it was very difficult for scientists to believe that that was possible for a wave to propagate in the vacuum. It was very difficult, and it generates all sorts of fallacies and incorrect theories. Okay, this mindset of thinking that a wave required a medium to propagate generate all sorts of incorrect theories that we're going to discuss even in more depth in Physics 7. Okay, but here you go, earthquakes. Okay, earthquakes is a wave too. Is a wave that propagates along the crust of the Earth. Okay, and we have, and this wave has enough energy to destroy buildings, right? And then we have this special type of wave that does not require any medium to propagate whatsoever. And this special type of wave is called electromagnetic wave. It's light, basically, it's light, visible light, infrared light, ultraviolet light, X-ray. X-ray is a type of electromagnetic wave, gamma rays. We also have we also have the waves of your radio station. Okay, that is also an electromagnetic wave. Until the end of the 19th century and the beginning of the 20th century, we thought that light, and electromagnetic waves in general, required a medium to propagate, for instance, from the sun until the earth. So scientists, they start to build models that there was something in the vacuum surrounding us, a special type of medium that they call the ether. Okay, and eventually that generated a huge confusion in among the scientists at the time, and which ended up with a revolution in physics, which resulted in a revolution in physics. And Einstein was part of this revolution. Okay, so in addition to light or electromagnetic waves, we have another important type of wave that was demonstrated just recently. It was predicted by Einstein himself, but it took 100 years for us to detect, to obtain experimental evidence of this type of wave, a wave that does not require any medium whatsoever to propagate, and the name of this wave is the gravitational wave. Okay? And people won the Nobel Prize for, here for the detection of gravitational waves. Let's take a look at the gravitational waves. Okay, new theory of gravitation holds key to the early universe. Okay, gravitational waves are waves of space-time distortion and curvature that propagate at the speed of the light. So think about that the gravitational wave is a distortion in the space-time continuum. It's a distortion in the volumetric, in the 3D, not the 3D, but the 4D. Now, in the four-dimensional space. Okay, they were proposed initially by Oliver Heaviside, okay, and then later by Henry Poincaré. But it was Einstein himself that came with the full theoretical description of those gravitational waves. I'll give more credit to Einstein than those two, even though those two guys, they are very smart as well. Okay, gravitational wave. Let's take a look at Nobel Prize. I believe that they won, 2017. See that? The 2017 Nobel Prize in Physics was awarded to Rainey and Weiss, Barry Barish, and Kip Thorne for their decisive contributions to the LIGO detector. The LIGO detector is the experiment, the huge experiment that they put together to detect gravitational waves. They were recognized for confirming Albert Einstein's century-old prediction of space-time ripples detected by the Laser Interferometer Gravitational Wave Observatory. That LIGO stands for Laser Interferometer Gravitational Wave Observatory. And we have one of those here in the States. Okay, let's see where these guys are from. I believe they're from Caltech. Let's take a look here. No, Cambridge, Massachusetts. He died recently. Wow, just recently, August 25th. 2025. Most likely this guy was from MIT, I believe. Let's take a look at him. And Massachusetts Institute of Technology, yeah. But there must be someone from Caltech here too. Maybe the other two guys, one of the other two guys should be from Caltech. Let's see, this guy, Nobel Prize in Physics, Caltech, yeah. See that? And Barry Barish, the other Nobel Prize winner. He was born January 27, 1936. Okay. And he joined the faculty of, University of California, Riverside. But did he? I suspect that he was from, let's see, at the University of California, Berkeley. Okay, so he's not from Caltech, apparently, huh? Honors and awards. Okay, family. Yeah. So this guy worked in the LIGO as well. Okay. Oh, let's see. Emeritus. He's an emeritus at Caltech. Okay. He's an emeritus professor at Caltech. But he joined the faculty at the University of California, Riverside in 2018, just 1 year after the Nobel Prize, becoming the university's second Nobel Prize winner on the faculty, the University of California, Riverside. We have a bunch of Nobel Prize winners at Caltech, okay? And let's see the other guy, Kip Thorne, right? Kip Thorne, theoretical physicist. Let's see, a longtime friend and colleague, Stephen Hawking and Carl Sagan. He was the Richard Feynman professor. This guy's from Caltech. He was the Richard Feynman professor of theoretical physics at Caltech. Caltech in Pasadena. He must have since they're saying that was right in the past. Oh yeah, he died. Oh no, he's still alive. Age 85. He's still alive. Okay, so those are important waves to keep in mind. Okay, so in order to create a wave, you must disturb a medium. That's the best way and the medium for electromagnetic waves is the vacuum. The medium for the gravitational waves is the four-dimensional space-time. Okay. In the case of the wave of electromagnetic waves, the medium actually is the electric and magnetic field. We can say that. Okay, so we say that light is a disturbance in the electromagnetic field, whereas gravitational waves is a disturbance in the space-time continuum. So you must have a disturbance to create a wave. That's the case of the string in the of your guitar. Okay, you pluck the finger in the string of your guitar, you create a wave. You pluck the finger at the surface of body of water, you disturb the water, that's the medium, and you create a wave. Okay. What else do you have to know? You have to know there are two types of waves. One, transversal waves, okay, and longitudinal waves. And by transversal wave and longitudinal wave, this is exactly what it means. I'm going to give you an example of transversal wave. Waves along a string, okay? Let's take a look at my simulation that we saw before. Here you go. Okay, here is my string propagating along my wave propagating along the string, right? So let me just go back here in time and run my simulation again. Here you go. The disturbance, when you put the thing to move, right, you can see the wave is propagating along from the left to the right. Okay, but the disturbance is transversal to the propagation of the wave. Do you see that? The disturbance, the disturbance along the string is up and down. It's not along the horizontal direction, but it's up and down. Just like you move your string or your rope up and down, the disturbance is perpendicular to the propagation of the wave, and that's why we call it a transversal wave. Okay. Another wave, you get a coil, right? The coil acts just like a string. You move one end of the coil up and down, you produce a transversal wave. Waves along a coil that moves up and down, but the coil also can be used to generate longitudinal waves too, okay? Another type of wave that's transverse is the electromagnetic wave. The electric and magnetic fields of light, X-ray, gamma rays, UV radiation, infrared radiation, radar too, right? Radar signals, they are a type of electromagnetic wave. You know, the vectors of the electric and magnetic field, they move perpendicular, they oscillate perpendicular to the propagation direction of the wave, okay? So I'm gonna waves along the string, the motion of the infinitesimal masses, infinitesimal sections, right? Infinitesimal sections of the string is transversal to the direction of propagation of the wave. 90 by transversal we mean 90 degrees. Okay, 90 degrees. That's what we mean by transversal. Here's the same thing. See above, since the coil is now behaving as our string, okay? And in the case of the light waves, and we do have a simulation in physics, you know, electromagnetic waves is something very difficult to visualize, okay? But you can visualize in a very abstract sense by using vectors. And there is a nice simulation here, physics simulation in the internet. Let's see, simulations online. that shows an electromagnetic wave. Let's see if I can find it. It's not fat, not fat. Maybe fat has. So let's see. But I'm looking for another one that I like. My physics lab. Let's see if FET has a simulation of electromagnetic waves. Let's see, physics, right in here. Let's see, electricity, electricity, magnets, and light and radiation. Let's see if they have one here. Oh, yeah, it doesn't look like they do. I believe this, I believe it's Fender. Fender, let's see. Well, Fender, maybe this guy here. Walter Fender, Apps of Physics. Okay, yeah, that's the one. Fender. Electromagnetic waves. It's all in Portuguese. Let's see if I can get that in English. That should be that one should be in English. No, that's Portuguese. English, English, English. This one here that I want. Yeah. Oscillations and waves, electrodynamics, electromagnetic wave, right in here. Okay. The electric and magnetic fields of a wave can be described as a vector. Okay. Those in red color are the electric fields. And the one in blue color is the magnetic field. Do you have the illusion that we have a wave propagating from the left to the right here? Okay, and again, the disturbance in the electric and magnetic fields is perpendicular to the direction of propagation of the wave. Okay. Which other waves are transversal waves? I can give you two more examples. They're not all that you're going to see, right? They're not all of them, right? But water waves. Water waves are transverse waves. Light waves are electromagnetic waves. In this case, the electric and magnetic fields oscillate in a direction perpendicular or transversal, right? Perpendicular or transversal to the direction of propagation of the wave. Water waves are transversal as well, and some waves associated with earthquake. Okay? Some waves associated with earthquakes are transversal, others are longitudinal waves. Now, how are longitudinal, which is an example of a longitudinal wave, okay? Here you go. Sound waves. Sound waves is a longitudinal wave, and I have a nice simulation here that I prepared. Let's see, is of a sound wave. Let's see here, sound right in here. Okay, so what do you have here? What do you have here? All those points that you see here in my graph, okay, they represent air molecules. Okay, oxygen, nitrogen, that's what they represent. And when we start talking, with our vocal cords, right? Our vocal cords, when our vocal cords vibrate, the vibration of our vocal cords introduces a disturbance in the air, in the medium. That's the air. and this disturbance propagates from the source, from my vocal cords, all around my environment, okay? And how that is this propagation goes, okay? This propagation is depicted here as pressure waves. Notice that there are some places here in this medium in which the air molecules are closer to each other, right? That's a region of high pressure. And then there are regions here in which the air molecules are very well are, are, are very distant from each other. That's a region of lower pressure. Concentration of our air molecules is high pressure. And when the air molecules are very far away from each other, it's a low pressure environment. Okay. And I can do the same simulation that I did before, that this sound wave can be, likened to that of a musical instrument, okay? The geometry here is that for instance, of a flute, for instance. And when we start doing the simulation, let's start the time t equal to 0, right? 1. No, it didn't work. Let's see. Let's see why it's not working. No, it's not. Someone's trying to get in. Yeah. When I prepared the simulation, it took me like 4 hours to prepare the simulation. Let's see what's going on here. There might be something odd with my sound wave. It looks like I think I know what happened. No, that's not the problem. Let's see this one here. Huh. That's a shame, enable content. That's why, but that might be the problem. Let's see if it works now. No, it's not working. Let's see, 10. Huh. Well, what a shame. This thing used to work so well. I want to. Well, in order for you to visualize, let's see if I have another one here. Yeah, let's see if it's another Tevas. I must have another document like that. Continue. This one here. Let's see if I have another one. I'm very proud of the simulation that I did. It took me a long time to do, but it was fun to do it. Let's see if it's oscillation, sound waves, or maybe it's this one here. Let's see if it's this one here. Sound. Let's see. Lambda 3. Okay. This one is working. Good. Did you see the change? Let's see. Okay. Doesn't look like I can do. Let's do every half second, right? Yeah. Looks like we have to do every 0.2 seconds. Let's start with 0. Okay. 0.2. Let's see here. It's a wave that propagates in the incorrect direction. Let me change it here. I'm changing the sign of propagation of the wave so it can propagate from the left to the right. It was propagate. This wave was propagated from the right to the left. Now, you go. Let's see now. 0, right? 0.2. Yeah. Can you see the wave propagated from the left to the right? Now we're going to start 0.1, every 0.1. Here you go. 0.1. Do you see the wave propagating from the left to the right? 0.2, 0.3. And while you observe this simulation, pay attention to this larger dot that we have right in here, okay? Pay attention to this larger dot that you have right in here. 0.3, 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 1, right? 1.1, 1.2, 1.3. So do you get an idea what's happening to this big point that is in there? This big molecule of air, right? That is in my simulation. You know, this big one that you see here is just oscillating back and forth. It's not moving with the wave, okay? It is just like the transversal vibrations of my string, of the pieces of my string, right? It's not moving with the wave. It's just vibrating about a position of equilibrium. Every one of those molecules here is vibrating about a position of equilibrium. But the whole set gives you this illusion that there is something moving from the left to the right, okay? And now I'm going to rewind my movie, right? Here you go. My movie is rewinding to the left, and I'm going to play it again. Here you go, time t equals to 0. And look what happens. Here is my longitudinal wave. In the longitudinal wave, the particles oscillate in the longitudinal direction. The medium oscillates in the longitudinal direction. Okay, let's rewind it again. Let's rewind it again. I'm going to play it again. And again, watch this big molecule here that I put here. I made it larger so you could see, you could have an idea. You could understand that it's not the medium that's moving from the left to the right, okay? Because each of those point particles in there, they are oscillating about the position of equilibrium. And this whole set oscillating about the position of equilibrium gives you this illusion that there is something propagating from the left to the right. But it is not just an illusion, okay? It is something that's really propagating from the left to the right. Because if my sound waves were not propagating from the left to the right, for instance, you wouldn't be hearing, you wouldn't be listening to me, okay? So let's go ahead and simulate it again. Here you go. Okay, the waves, this part here of the wave, we call it the crest of the wave. Okay, that's the crest of the wave. This region here of lower density, we call the trough of the wave. Okay, and again, the crest. The valley, right? Trough of valley, crest. And here we have something, we have the same thing here. Okay, let's simulate this one. Here is my string, right? This one is a better one. Let's see. 1, no, 1, no, we gotta do half. Let's do half. Half, yeah. And again, this wave is propagating to the left. That's because of this sign right in here. If I change the sign to a negative sign, then the wave is going to propagate to the right. Okay. And we're going to get into the mathematical relation that I use here. The theory is mathematically is very simple. Rather simple, okay? Here you go. Let's start. Half second, right? Let's see. Yeah, that's good. Half second, 1 second, 1.5 seconds, 2 seconds, 2.5 seconds, okay, 3 seconds, Watch for those two dots, right? Those big dots. Those big dots, they are just oscillating back and forth. They're not moving with the wave. The medium does not move with the wave, okay? It's the energy that's moving along the medium. 3 seconds, 3.5 seconds, 4 seconds. I want to go as far as I can. 5, 5.5, 6, 6.5, 7. Let's go until 10, right? 7.5, 8, 8.5, 9 seconds, 9.5, and 10 seconds. Now I'm going to rewind my movie, undo, undo, undo until I get to t equal to 0. Okay? Until I get oh, it looks like I got it. Yeah, right in here. I overshoot. And now I'm going to play my movie again. Here you go. Those big dots, they are exactly at the same horizontal position. They are not moving with the wave. It's just the wave that's moving. The material medium is just oscillating in the transversal direction of propagation of the wave. Okay? So we run out of time here of simulation. And here is the crest of the wave. And here's the valley of the wave. And here's the position of equilibrium, the node. Okay? Our wave has a crest. Here you go. Longitudinal wave. And I showed the longitudinal wave simulation, right? The idea was to just show you the simulation here of the longitudinal wave, but now we are talking about the elements of the wave. Now let's go some more other examples. Most of the waves out there are transversal. We don't have many longitudinal waves, okay? A wave in a coil that's compressed and distended, you know? Think about a coil that we compress, right? A long coil that we compress at one point or extend at another point, we release it, and then we have this wave propagating along the coil. And some waves associated with earthquakes. Let's take a look. Earthquake waves. Earthquake, earthquake waves. Let's see here. I want to go to Wikipedia. Wikipedia, seismic wave. Okay. Okay, so there are different types of seismic waves. Let's see if you discover this. Body waves. Body waves travel through the interior of the Earth along paths controlled by the material properties in terms of density and modules. You have the primary and secondary waves. Okay. Primary waves, P waves, are compressional waves. What do we mean by compressional waves? They're longitudinal in nature, right? You compress the medium, right? And you can also distend the medium. So there are those body waves of the earthquakes. There is the primary wave and secondary wave. They both have different speeds. Okay, primary waves are compressional waves. The primary waves are longitudinal wave. Let's take a look at the secondary wave, shear waves. That shear waves is a transverse type of nature, a transverse type of wave. Okay. Which other? Surface waves. We have surface waves as well. And then we have how many surface waves? 1, 2, 3, 4. Wow, we have 4 surface waves. Normal modes, okay. No, three surface waves. Stoneleigh waves, law of waves, right? And Rayleigh waves. And the surface waves are what? Mechanical surface waves. It doesn't say whether it's a transversal wave or longitudinal wave. Okay. So those are examples of waves. A wave, think about that, we can have waves that are propagating the one-dimensional space, a wave that propagates the two-dimensional space, and a wave that propagates in three dimensions. Okay, the easiest one to visualize is the 1D wave. This wave that you see right in here is a one-dimensional wave because the wave is propagating just one direction. Here too is a one-dimensional wave because the wave is propagating in one direction. But a wave in the surface of a pond is a two-dimensional wave. Okay? You disturb the surface of the pond and you see that circular wave propagating from the center. Is a 2D wave. And 3D wave is more complicated, okay? Like an electromagnetic wave, a point source of light generates a 3D wave. It generates spherical waves, okay? Here you go, 1D wave example. Wave in a string, along a string. Let's see, delay is trying to come in. Good. Wave along a string. The velocity vector, it has a 1D velocity vector. Okay, what about 2D waves? Waves in the surface of a lake, right? Think about disturbing a point in the surface of the wave of the lake. If you do that, you generate a circular wave, several circles that move away from the center, or several circles that move away from the disturbance point. Okay, and then we have 3D waves. One example would be as the wave of a point source. Okay, that generates a spherical wave. Another example would be a light source, right? A point light source. I mean, a point light source. That's what I mean here. A wave as a wave generated by a point light source. Can also be not just a point light source, but can also be like a point sound source. Think about a spherical speaker, right? That can oscillate back and forth, like in a spherical speaker that can oscillate there inside. It's gonna generate a spherical wave around it. Okay, so don't forget the simplest one is the 1D wave. This is the simplest type of wave. This is the simplest type of wave to visualize. Okay. What else you have to know about the wave? Yeah, components of a wave, elements of a wave, right? Let's talk about elements of a wave. Elements of a wave. One, the node is a point that is at the equilibrium position, okay? Equilibrium position. just like you saw for this wave right here. Here is a node, here is a node, here is a node, here is a node. A node is that point that is at a position of equilibrium. At the position of the position of equilibrium. Position, oh gosh, of equilibrium. Okay, we have a node, but we also have a crest. The point of maximum amplitude of a wave. Maximum amplitude or displacement, right? Or displacement. Not of wave, but of the medium, right? Of the medium. Maximum displacement of the medium, equilibrium. Why is equilibrium here? Let's see. Yeah, I don't know. Medium. Yeah. Here's a crest of my wave. Okay, in the case of the sound wave, the crest of the wave is this position here of maximum pressure. Okay. For a wave in a string, comma, the peak position is the crest. For a transversal longitudinal wave, okay, the point of maximum compression is the crest. Okay. Valley. Oops. Valley. The point how do you say that? Here you go. Of minimum amplitude. Yeah, let's say minimum amplitude. Okay. The point of greatest, okay, negative displacement. Let's put it this way. Valley. They also call it a straw. Let me make sure it's a value of a wave. Valley of a sound wave. I believe they also call it a straw. Yeah, straw of a wave. Right? Straw of a wave, the lowest point, the valley between two crests. Okay? Yeah, that's another word for this negative amplitude. And let me give you again a illustration, right? For this wave, here's the position of straw of the valley. Valley. Okay? In this case of compression wave, is going to be the point of maximum rarefaction. Okay? Let's write it down. For a sound wave, comma, the point of maximum rarefaction is the valley or straw. And we have more, okay? Those three are very easy to memorize. There is no challenging understanding that, right? But then we have other things. We have amplitude, right? Amplitude of a wave, point of maximum displacement, point of maximum displacement, distance of maximum displacement, In my case here, the distance of maximum displacement is 0.4 meters. That's the amplitude of this wave. It's 0.4 upwards, 0.4 downwards. Okay. We also have the distance from peak to peak. Is a very important quantity. The wavelength of a wave distance from peak to peak. From crest to crest, right? Let's put here. From adjacent crests. Better. Amplitude of a wave is usually represented by the letter A. The wavelength of a wave is usually represented by the Greek L. The Greek letter L, and Greek letter L is called lambda. That's how we represent the wavelengths of most waves out there. It's almost a standard definition. Almost every book represents wavelength by this letter here. But a wave also have a period. Okay, period of oscillation. Just like a simple harmonic oscillator has a period too. How long it takes for the point of oscillation to go back to the same spot. Okay, let's see if I have a full oscillation here. In this case, I have T at 19, right? Let's go back in. Oh, what did I do here? Let's go back in time. Let's see. Watch, we're going to get to 0, right? So watch for this extremity here of my wave, okay? It's going to go down and then it's going to go back. This period, the amount of time it takes to go back to the initial position is the period of the wave, okay? So let's play the movie and let's watch the time, T. Going down, reach the trough, right? It seems to be the period is going to be 7 seconds for this one because we reached the bottom at 3.5 seconds. Do you see that? It's going to go up, 6, 6.5, 7. A little bit less than 7. A little bit less than 7 because it overshoots the peak, okay? So this wave has approximately a period of 7 seconds, which corresponds to a full oscillation of the wave, okay? So those those are the 3 important elements of the wave: amplitude, wavelengths, and period of oscillation. Related to the period of oscillation, we have the frequency, okay? And the frequency of the wave is given by the inverse of the period T of oscillation in seconds. The frequency and the unit of frequency is 1 divided by second, which, by the way, we call it the hertz. Can you remember that? Okay. Frequency is just a different way of talking about the period of a wave. But related to the period, we also have something else that we call the velocity of the wave. Velocity v of the wave. And the velocity v of the wave is related to the wavelengths and the period of the wave. Lambda divided by the period of the wave is the velocity of the wave. Another way to write that down is lambda times the frequency. Lambda times the frequency. Oh, here you go, like that. I want the italicize here. You know, italicize so you can look nicer. Look nicer. 3:44. We are going to have our break very soon. Remember those important parameters of a wave, right? Let's see here, parameters of a wave. Let's put parameters of a wave. And then we can start remembering. We start at 1. Yeah, here you go. That is 10:45 now. Let's take our break. Break between 10:45 a.m. and 11 a.m. Okay. See you in 15 minutes. I am back here. 15 minutes, and let's continue with our lecture. Okay, so far we're talking just about the concepts of the wave, right? But we're gonna have some math to introduce here for you. Okay, so let me just what you see right in here for a one-dimensional wave. For a one-dimensional wave, we can describe it mathematically. Here you go. Let's write that mathematically. We can describe a one-dimensional wave in the form as a function of x and t, right? Here you go, like that. The wave, a one-dimensional wave, must be dependent on the x position and must be dependent on the time as well. Okay? But more specifically, it can be expressed and but more specifically, it can be expressed in the following way. Either, okay, one, either as a forward propagating wave. See that? A forward propagating wave has a negative sign here, which is x position, right? Along the x coordinate minus vt. Vt is the velocity of the wave. Okay? Or either as a forward propagating wave or continue numbering. Let's see. Oh, it takes so long. Or why did he put 4 here? Restart. Set numbering value. It's easier to set numbering value. Or 2. Oh man, takes so long. And when it 2, here you go. Can you place a 2 there for me? Yeah, okay. Or as a backward propagating wave. And the backward propagating wave has a positive sign here. Sounds like strange, right? But that's exactly how a forward and a backward propagating wave can be described. So any wave that has this genetic functional format will be a forward propagating wave and or a backward propagating wave. Okay? Examples of forward and backward propagating waves. Now I'm going to be even more specific. Okay, so here you go. That wave that I simulated for you in Excel, okay, this wave that you see right in here is a cosine wave. Okay, it's a cosine wave. A time t. Okay, so here you go. Let's put the cosine wave. The one we simulated in class. It's a cosine wave. For time t equal to 0 and for the position x equal to 0, the cosine is going to be 1. The argument is going to be 0, right? The argument of the cosine is going to be 0, but the cosine is going to be 1. And then you're going to have that y, the position of the wave, right? Along the y-axis is going to be the amplitude y0. And that's exactly what I have here. Let's take a look at this one, okay? See that, the equation? Can you see the equation there at the top? Cosine of 2 pi over lambda times x minus vt, okay? F here corresponds to the velocity. T corresponds to the instant of time that we have here. And x is b2, okay? Along the x direction at a specific instant of time, we have this sinusoidal function. That's the most important wave. This is, although there are more waves out there that can be expressed in different functions, comma, the trigonometric waves are the most important ones. Okay, why is that? Why is that they are the most important one? There's a reason why they're the most important one. They are the most important ones, because a summation of different sines and cosine waves can express any type of wave. And by any, I mean, it's not just a sine or cosine waves. By any type of wave, I mean a triangular wave, for instance. Other types of waves. Other types of waves. Triangular wave. Square wave. Square wave. Okay. You can have a pulse. pulse wave is just a hump, a single hump that propagates. Okay? So all those type of waves and more, right? And more. And more. And others, right? Can be expressed as a linear combination of sine or cosine waves. Here you go. And here I'm going to put, different amplitudes. Different amplitudes. See, I am summing up different sine or cosine waves. And by the way, can be either sine or cosine, okay? Can be either sine or cosine because they're almost the same function. It's just a matter of a difference in the argument. And by the way, these trigonometric waves are also called plane waves. Okay? Plane waves. So every time that you hear the word plane waves, you already should know that it's a cosine or a sine function. Okay, here you go. Here's a forward propagating wave. And this one here is a backward propagating wave. Oh, 1, 2, 3. Here you go. I gotta change the amplitude as well. And by the way, what this K represents, right? I didn't tell you what this K represents. Let me write it down right in here. Where? Here you go. I should write that for you. K is equal to 2 pi divided by lambda, divided by the wavelengths, right? And let's not forget the V. You already know what V is. Hopefully you have already memorized it, right? It's not difficult to memorize the V. Is the distance divided by time, right? And the time should be the period of the wave, the period of the wave. How do we calculate the period of the wave? It's not difficult to calculate the period of the wave. Okay? It's not difficult. Going back to my wave right in here, right? A full period is going to be a y value that will coincide, right, with the previous one, okay? To find out the period of a wave, not just the period of a wave, but the period of a harmonic oscillator as well, right? Let's find to find the period of a wave, you must use the mathematical definition, the period of a wave, or let's see, or the period of an oscillator, of an harmonic oscillator, right? Harmonic oscillator. You must use the mathematical definition of the period itself. Let's do that for the harmonic oscillator first. And then I'll show you how to do that for the wave. It's not difficult. Once you understand how to do the period of a harmonic oscillator, you have to go to the definition here, right? Here you go. I'm gonna get for all those three here, for the harmonic oscillator, for the simple pendulum, and for the physical pendulum. The techniques are exactly the same. Simple harmonic oscillator. For SAA, for simple harmonic motion, right? That's the equation. The period of the oscillator is going to be that instant of time, right? It's going to be not the period instant of time, it's going to be that amount of time in which this relation here equals this other relation here, right? That's the condition for the period of a simple harmonic oscillator, like that, right? That would be, here would be the period. We should put the lower, like the genetic T in front. Let's put the genetic T in front here, right? That should be the same amplitude, right? It's just the full vibration. And we can use this equation. Here you go, x naught cancel with x naught, right? And we can even make t equal to 0 here. Making t equal to 0. Making t equal to 0. We can find capital T, the period, more easily. Okay, if we make t equal to 0, the cosine becomes 1. Here we end up having a simpler equation, right? And this term here in the parentheses must be equal to what? Must be equal to 2 pi. That's how we find the period of the oscillation. Okay? Here you go. And then we solve this equation for t. We end up with use the ratio here inverted. Okay? That's for the simple harmonic oscillator. You do the same thing for this one here. For the simple pendulum, the period is K must be replaced by G, M must be replaced by L, right? K must be replaced by G, M must be replaced by L. And by the way, we usually put the 2 pi in front of here, so it looks nicer. For the physical pendulum, the period is, what do? We replace K by MGL, right? Or we replace G by MGL, either one. G by MGL. We replace L by I. They're exactly the same parameters, right? It's just a different letter in there. Mathematically, they behave exactly the same. And we do the same to find, now that you know how to find the period of an oscillator, now it's straightforward to find that for a wave, okay? Now it's gonna be, to find the period of a wave is going to be straightforward, right? I'm gonna use this one here, the simpler one here. Here you go. To find the period of a wave, we do something similar. With just one additional step. And the additional step is what? Make initially x equal to 0. Okay? Make this x equal to 0 here, right? Because we are taking, don't forget, we are taking a full period of oscillation, right? So we can choose this point here in our diagram. We could have chosen it here too, but it would be more difficult to do the math. Okay, we could have chosen this one here. We could have chosen this one here. We could even have chosen this one here. But it's much easier mathematically to choose this one here at x equal to 0. Okay, at x equal to 0, we have this relation. Okay, minus kVt minus kVt. But cosine of minus kVt is equal to cosine of plus kVt, right? No big deal here, you know that from regular trigonometry. And now to find the period, this guy here must be equal. This equation here must be equal to this other equation here. We must have this equality, just like we had before for the simple harmonic motion. Here we go. Let's see. Okay. Here you go. I'll place right in here. That's the equality that must hold. If we solve this equation, we can find the period. Our first step is to eliminate y naught. I'm gonna take out this positive sign too, so you can. I'm gonna make t equal to 0. Okay, when I make t equal to 0, it becomes simpler to find out what the period is going to be. Cosine kv0 is 0. This one turns out to be something like that. Next step. This one's going to be 1. And in order for this term to be equal to 1, kVt, kV capital T must be equal to 2 pi. Okay, and we find that our period is going to be kV. I can go another step. K is 2 pi over lambda. 2 pi over, right, like that. We can go ahead and simplify, cancel 2 pi with 2 pi. When you cancel 2 pi with 2 pi, we can invert lambda. Lambda that's divided here downstairs can go upstairs. Okay, and look what we get. We get exactly what I told you before, right? That the velocity of the wave is the lambda divided by the period. Okay? Here I just told you I didn't prove mathematically, but I'm proving that mathematically right now. Okay, so can you remember that? That's the most important equation for the wave is this one here. This one, not this one, this one here, right? Either the cosine or sine, okay? Doesn't matter. Doesn't matter. Because one is going to be equal to the other just by, for, you're going to have a phase difference only, right? That, let's take a look at the book. What we are doing here, and I also going to chapter 16. Here you go. Let's see. How do I quick access login? Let's hope it doesn't take too long. Yeah. (11:26) Physics 6 fall 2025. Wiley course. Okay, we are talking about chapter waves and sound right here. Okay, we cover nature of waves. It's a traveling disturbance, And then a wave carries energy from place to place. This is energy propagation. Periodic waves. You go. I discussed that as well. From crest to crest is the wavelengths, right? But here he's taking from every other node, but you can also take it from adjacent crests, the distance between adjacent crests. It's either the wavelengths or the period, right? Would be the wavelength if you're plotting the y-axis along the x-axis, but it would be the period if you're plotting the y-axis versus time. In either case, it's going to be a sine function for a given x, here for a given instant of time, and here for a given x position at a particular location at a particular instant of time. Okay, here we have a train that behaves like a wave. The analogy for a traveling wave. It's this train is like a square wave. Oh, this is an interesting example, okay? AM and FM radios are transverse waves consisting of electric and magnetic disturbances, just like I mentioned before. And because they are electromagnetic disturbances, electromagnetic waves, they propagate at the speed of light, 300,000 kilometers per second. A station broadcasted an AM radio wave whose frequency is, that's the frequency of your, let's say, your favorite TV station, right? 1,230 kilohertz, or let's say 1.23 megahertz. Find the distance between adjacent crests in each wave. If you know the frequency, find what's going to be the wavelengths. Okay? You use this formula here. You know the frequency, you know the speed of the wave. It's a radio wave. You can solve for lambda. The speed of a wave in a string, we're skipping it, okay? That's a rather complicated, it's not the, how can I tell you? You know, actually, we can talk about that. We can talk about that. It's not, what you see right in here, what you see right in here, the relation that you see above for the speed, let me copy that. We can actually, you know, the relation we have above for the speed of a wave is the genetic relation. What do I mean by genetic relation? Any type of wave obeys this relation, okay? Any type of wave, I mean, whether it's a electromagnetic wave, whether it is a sound wave, a wave in a string, comma, an electromagnetic wave, a water wave, etc. However, comma, each of these distinct waves have a particular equation for their speed, okay? The chapter, you know, talks about specifically the speed of the wave in a string. It's possible to derive its speed, okay? But I'm not gonna do the derivation here because it's too much work. And if you need to know the relationship, you just look at the formula right in here, okay? That's the formula for the speed of a wave in a string, okay? For the speed of a particular equation, for instance, for instance, for instance, one, the speed of the wave in a string is given by the following equation. Like that. It's going to be a square root. It's going to be a square root. Okay. And what goes up here is going to be a force F. And this force has a name. This force is the tension in the string. Okay. And what goes downstairs here is going to be the mass per unit of length of the string. In the above equation, F is the tension in the string. The larger the tension, the faster the wave in the string. M is the net mass of the string, and L is the net is the mass of the vibrate. Let's put here the vibrating length of the string, okay? And L, not the length, sorry, M is the mass of the vibrating string. You go. The vibrating. And L is the vibrating length of the string, okay? And it's not difficult to remember that. Just recall that the stronger the force, the faster the speed, right? The faster the wave propagates. And the larger the inertia of the string, the larger the mass of the string, the heavier the string is, the more difficult it is to make it to speed up, right? But it's not just the mass of the string, it's actually the linear mass density of the string. Okay? That's one. And by the way, this equation that you see here is going to be equal to the other equation that we saw, okay? It's going to be equal to this relation here, to the genetic relation of the speed. I'm going to give you another example. Instead of a string, let's talk about electromagnetic waves. For an electromagnetic wave, okay, what do we know? For an and it's possible also to prove that, but it requires advanced math. For an electromagnetic wave, its speed is given by the following equation. Is going to be, the electrical and magnetical properties of a medium, okay? Those electrical and magnetical properties of a medium is given by epsilon, okay. No, yeah, epsilon, epsilon. Gosh, how do I call it? Epsilon. Yeah, epsilon. Why is not, let's see. Epsilon, is I here, right? Nope. Oh. Ha. Okay, good. Is the electric permittivity of the vacuum times the magnetic permeability of the vacuum. It's possible to derive this equation for an electromagnetic wave. But again, just like I said before, it's very difficult. For water waves, let's take a look at speed of a water wave. The speed of a water wave. Speed of a water wave is given by the acceleration of gravity times the depth. Okay? The speed of water wave varies greatly depending on the wavelength, water depth, and wave type, but generally ranges from slow ripples to fast-moving tsunamis in deep water, slowing and growing taller as they approach. For wind-driven waves, speed is linked to the wavelength and period. With longer waves traveling faster, calculated at approximately 1.56 times the period. For deep water. For deep and shallow water, right? For shallow water is the square root of G times the depth. Okay? For shallow, I'm going to copy that. For water waves in shallow water, it's the speed is given by G, right? And what's the other one? The depth times the depth. And just like before, the wavelengths and the period are related to this specific speed, right, of the water wave. Did you get the idea? Okay, so there is the generic equation for the speed, and then there is the particular speed equation for the speed in terms of other parameters. Let's see if I can restart. Yeah, good. Restart was 2. This one is going to 3, and so on. Okay, we can. There are many other set numbering values. It takes so long to. Okay, good. And so on. And so on. That's what this chapter is all about. They don't go into those details of the electromagnetic wave and the water waves, but it's a very nice parallel to keep in mind so you can understand that one equation should be equal to the other one. The generic equation should be equal to the particular equation. Okay? Right in here. Mathematical description of the wave. Okay, so I covered that. And what you have here is exactly the same thing that I covered. Okay? He's just putting with different parameters here. He's putting the frequency, right? He's writing down the frequency. 2 pi over lambda is the K. 2 pi over lambda is the K, okay? Kx minus Vt. Okay. Forward propagating wave, backward propagating wave. So we covered that. Nature of sound. Sound is a longitudinal wave. Okay, and that should be, here go this link that I told you, right? This link is a very good analogous of the sound wave, of a sound wave. We have a region of compression of this link, and we have a region here of air of high pressure, where you have the condensation of air. They call it condensation of the air. I don't like that. Okay, and then you release, and that's how a speaker works. It compresses the air nearby it, and this wave goes propagating. If you are talking about a sinusoidal wave, you're going to have multiple regions of rarefaction and condensation. Here you go. Rarefaction and what they call, I like to call it compression. Here's the region of higher amplitude or higher pressure. The distance from between adjacent regions of higher pressure is going to be the wavelengths. Okay, that's how the sound frequency, blah, blah, blah. Okay, there are other waves or other types of waves. In addition to sound waves, we have infrasound and ultrasound waves, right? So let's talk about that too. That's important. Okay. We have sound waves, ultrasound waves, and infrasound waves. we humans cannot pick up those two types of waves. We can pick up only these two types of waves. Our detectors, right, which is our ear, which is our hearing detection system, pick up waves of only a given frequency. Okay, keep that in mind. Our sound detection system, okay, the hearing system can pick up only certain wavelengths of sound, the ones that sit between 20 hertz and 20,000 hertz. Okay? Is that difficult to remember? That's easy, right? Between 20 hertz and 20 kilohertz. Let's take a look. I want to double check that. Confirm this value. Let's see. The book doesn't have it. Okay, and frequency of sound waves. Yeah, 20 hertz and 20 kilohertz, right? Anything below 20 hertz is called infrasound waves. Anything likewise, anything above 20 kilohertz is called ultrasound. Make sense? And some animals can detect sounds in those regions that we cannot detect. Sound frequency sensitivity of elephants, for instance. Yeah, see that? It's highly sensitive to low frequency sounds. So elephants, they are sensitive to infrasound frequencies. 14 to 16 hertz, all the way up to 100 hertz for long distance communication, right? Detecting through the air and ground vibrations via their large ears, feet, and trunks. While their high frequency hearing is less acute than humans. So they go only up to 12 kilohertz. Humans go all the way up to 20 kilohertz. What about dogs, right? Dogs. Dogs have superior sound frequency sensitivity at high pitches, hearing from about 65 hertz. Humans can go all the way down to 20 hertz, right? Dogs cannot hear below 65 hertz, but they can go all the way up to 65,000 hertz in the ultrasound region. Okay, and that's almost time for our break, right? 11:45. Let's take a look here at the book. Sound, the speed of the sound. Oh, yeah, you gotta know the speed of the sound, right? The speed of sound is that's the equation. You don't need to memorize the equation, but you have to know. You have to know that the speed of the sound is around 300 meters per second. It's very fast. Sound travels very fast. The speed of the sound is around 300 meters per second. Okay. So now, here you go. We have those chapters here on those sections on chapter 16. We're not going to cover speed of sound. We're skipping that, okay? So let me take out the bold face here. Any questions about that? Nature of waves, periodic waves, speed of a wave on the string, mathematical description of a wave, this nature of sound. Nature of sound is a longitudinal wave. That's what you have to know about the nature of sound. And all those waves, whether they are transverse or longitudinal, they have a similar mathematical treatment. Okay? It's going to be either a sine or cosine of kx plus vt. Kx kx plus kvt, right? I prefer this format, this mathematical format, because it's very intuitive. Let's see here. Yeah, I didn't cover that yet, but I prefer this format here because x minus or plus vt, right, tells you a lot about the equations in kinematics that we learned. Okay. So let's have our break now. I'm going to, it's not 200, it's 330 meters per second, okay? Break from 11:50, right? 11:50 a.m. to 12:05 p.m. Any questions? Okay, so I see you in 15 minutes. Okay, we're back here. And let's go back here. Come on. And those are the chapters of the section of chapter 16. Let's put everything, all the sections in the same place here for the final exam. The final exam is everything, okay? But there we will concentrate. But because those chapters some of the chapters didn't show up in the previous exam, I'm going to explain to you how we're going to do here. Here you go, chapter 11, right? Let's go. Those chapters that didn't show up in the partial exam is going to have a heavier weight in the final. Here you go, chapter 10. Chapter 10. Let's look for chapter 9. Here you go, chapter 9. We're going to copy that. Oops. And erase this one here. Let's look for chapter 8. Chapter 8, right here. Right? Copy everything here. 8, 7, 6. Seven, 6. Chapter 5, let's see, what's chapter 5? Chapter 8. Eight and 9. Chapter 6. Wow, chapter 6. I'm on chapter 5. Should be this one, right? I believe that's the one. Oh no, that's chapter 6. Okay. Most enforced. That's chapter 5. Okay. Chapter. Lots of things. We cover lots of things, right? 4, 5, 5, 4, 3. And then we have 2 and 1. Okay, right here. Two and 1. Okay, chapter 1, 2. 1 and 2 was for exam. Exam material up to, okay, excluding exam. Okay, chapter 1 and 2, right? 1, 2, exam 2, 3, 4, and 5, 6, and 7. Okay, so I'm gonna copy all of that. Go all the way down here. Material for the semester. So far, hopefully we'll be able to cover something else. One more chapter. Let's see if we can do that. Chapters 1, 2, 3, 4, 5. I want to, let's see how I'm gonna do that here. 6.1. Can I do that? Let's see if it works. No, doesn't look like it works. 6.2, 6.3, right? I'll let you figure that out. Okay, so 6.45. He kept the. It's a shame that let's restart from one. It's better. Let's see, restart. Yeah, okay. Quatro, cinco, 6, 7, 8, 9. Né? Section 1, 2, 3, 4, 5. We're skipping. Let's see. We can take chapter 8. Okay, I'm not going to renumber it. It's going to be too much trouble here. Let's see. Unless, let's see. Okay. Oh gosh. Continue numbering. Okay, good. Chapter 8. Chapter 9. Chapter 9. Chapter 10. Okay, and we gotta get 11 and 16. We skipped the 12, 13, right? And the others 11 and 16. And the situation is the following. We covered chapters 1 through 7 in the partial exams, plus labs 1 through 3, right? 1 through 3 in the partial exams. Everything else that we didn't cover, everything else that did not show in the partial exams, and I'm talking about chapters 8, 9, 10, 11, and 16, plus labs 4 and 5. Okay? We will have a larger weight in the exam, in the final exam. Okay, approximately, I would say approximately 50% of the questions will be on these chapters. And the other 50%. 1, 2, 3, 4, 5, 6, 7. You know what? Let's put 60%, okay? 60% here and 40% on chapters 1 through 7, okay? Okay, so we covered chapters 1 through 7 plus lab 1 through 3 in the partial exams. Everything else that did not show up in the partial exams, with chapters 8, 9, 10, 11, and 16 plus lab 4 and 5, we'll have a larger weight in the exam. Approximately 60% of the questions will be on these chapters and labs. Okay. so you can concentrate your effort. So you can plan to concentrate your effort. Okay, and we have another half hour to go. 12:20. We finish at 12:50. What comes next is an interesting chapter. I like to cover it. Okay, and that's chapter and whatever. Let's see here. Whatever plus chapter 16. Okay, and whatever we manage and whatever we manage to cover in chapter 17, right? Plus lab 4 and 5. So what comes next? Comes next is interference, or how waves collide. Okay, that's what I like to refer to this chapter: interference of waves, or how waves collide. We manage it. We manage to see this type of phenomenon, for instance, in the strings of a guitar, in the strings of a guitar, okay? The strings of a guitar generate what we call a standing wave. Okay, it looks like the wave is not going anywhere. You know, when you plug the string of a guitar, you know that you see the string vibrating up and down, right? It is as though that wave is just sitting there, not going anywhere. And because it looks like it's not going anywhere, we call it a standing wave. But in reality, what's actually happening is that we have very fast waves that are very fast propagating to the left, and another wave that's propagating to the right. And those two waves are interfering, are colliding with themselves, and giving the impression that it's forming a standing wave, a wave that's not traveling anywhere. That's what you have to keep in mind, okay? So when you pluck, right, the strings of a guitar, you observe a wave that just keeps on oscillating up and down, as though it is not moving at all. In reality, we do have two waves that are moving. One in the forward direction, one in the forward direction, and the other along the backward direction. And when these two waves collide, they give the impression that they form a standing wave that does not move anywhere. Okay? That's what, but in reality, they are moving. And what we have one wave that's moving to the left and the other one is moving to the right. And because we have those two waves, when they combine, when they collide with themselves, with the other one, they give the impression that they just standing in there, okay? We can treat this type of problem rather straightforward mathematically. we can treat this type of problem in a rather straightforward fashion. Straightforward way. Okay? Notice the following. We have a forward wave, right? Then I'm going to, that's propagating from the left to the right. And I'm going to put here y under f, subscript f for forward. Okay. And a backward propagating wave. A forward propagating wave and a backward propagating wave, which I am going to write like that. Okay, notice the forward propagating wave has a minus sign, the backward propagating wave has a plus sign. And I'm assuming that they have the same amplitudes, which is reasonable. Okay. When these two waves collide, we also say that they are superimposed. They are superimposed. Mathematically speaking, it is just like summing one wave with the other. Okay, so here you go. I'm going to writing down the resultant wave is going to be written in terms of the forward propagating wave plus the backward propagating wave. Okay, here you go. Resulting wave, right? Forward propagating wave, backward propagating wave. And there is a way to rewrite this equation. But before we rewrite it, I want you to remind you, right, that a more genetic way of writing down this relation would be in terms of those functions, right? Function of the forward propagating wave and the function of the backward propagating wave. Like that. Okay, so how can we rewrite? There's a way to rewrite that. Okay, there's a way to rewrite this relation here in an easier way of understanding it. Just recall that sine of kx minus kvt, right? Or sine of a minus b is sine of a cosine of b minus plus cosine of a sine of b. Remember, you learned this relationship, right? And the same, something else like that. Let's see. Let me write that down. Sine, I'm gonna write like that. A plus B, right, is sine of A cosine of B plus cosine of A sine of B. No T there. And we don't need to rewrite that. Applying, I have applied this. What you see right in here is exactly what you see right in here. Okay, let's keep on expanding this relation, right? Okay, cosine of minus something is going to be cosine of plus something. And sine of minus something is going to be minus sine of something. Okay? And now all you have to do is to sum those two functions. See, we have, let me go to another step here that I didn't. Here we go, I'm going to put the A in evidence, right? I'm going to put the A in evidence here. Okay, so now what you see right in here is exactly the summation of those two terms that you see here. Kx minus kvt, kx minus kvt, right? Kx plus kvt is kx plus kvt here. So all I have to do is to sum those two. Summing the two we have. Okay, so that's how we treat wave interference. Okay, well, I'm gonna get that. Two, see this one here cancels out with this one here when we sum those two. And we end up with just 2 sine kx cosine kvt. Like that. And now my resulting wave has a very nice, has a very simple mathematical interpretation. It's very difficult to interpret what you see right here, okay? So we have to rearrange those equations in an easy way to interpret it. So what we end up having here is the following, is 2a sine kx cosine kvt, like that. But I'm going to write it in a better way. That's going to make it even more intuitive than what you have here. I'm going to commute this term. Oh, the A, I keep the A there. Okay, I keep the A there. And now I recognize that what we have here is an amplitude that's vary as time goes by. Okay, what you have right in here, I'm gonna boldface it, is an amplitude that varies with time. I'm gonna write like that. Let's see, big AA. Now I'm gonna put B as a function of t. Okay, see here? That's what it's all about. This term that you see here is something that oscillates as time goes by. Okay, it achieves a positive amplitude 2a, right? And a negative oscillate between plus 2a and minus 2a. So as time goes by, you have this amplitude oscillating back and forth. And then as time goes by, and then you have here this function that's only a function of the position. And now you can see that you are going to have a sign that's going to keep oscillating back and forth, just exactly how you see it in the string, right? As it vibrates. And I have simulated something like that here. Okay. And I want standing wave. Here you go. Here's a standing wave. Here's is the one that we see in the string, right? When we plug the string. Let's see. Okay, so we're going to start at time t equal to 0. Okay, and let's see time t. Oh no, we gotta go at smaller steps. So let's see 0.2. Yeah, looks like 0.2 is too much. Let's try 0.5. Yeah, let's do 0.5. 1, 1.5, right? 2, 2.5 times t, right? 3, 3.5, 4. Can you recognize this type of motion, right? 5, 5.5, 6, 6.5, 7, and so on, right? And now I'm going to go back in time, and I'm going to play the movie from the beginning. 0. Okay, here you go. Time t equal to 0. Maximum amplitude. As time goes by, the string keeps oscillating back and forth. It's oscillating much faster than that, right, in real life. But here I can slow down time. Oops, what happened here? Okay. Okay, and now I'm gonna go back in time again. That's exactly what we see in real life, right? And that's exactly what I have here in my equations. Look what I have here in my equation. I have the amplitude, I have the cosine term with a time 2 pi, right? 2 pi f is the velocity, g is the time, e is the wavelength, lambda. And then I have my sine term, 2 pi, c, that's x, and e is the lambda, 2 pi over lambda x. Okay? And I can do, let's take a look at this one. Here's another interference wave, right? No, this one's not a good one. Let's see if I can get a different one. Let's see, 50. Yeah. And here's another mode of vibration. Here's going to be another mode of vibration. Okay, 0. I'm going to put a quarter so we can get more stuff here to visualize, more frames, right? 1, 1.25, 1.5, 1.75, 2, 2.25, 2.5, 2.75, 3. Now let's go back in time until we reach 0. This type of vibration can also be reproduced in the lab. It's not easy to reproduce that with the strings of a guitar, okay? But that can be done in the lab with strings and vibrators, oscillators, okay? So here you go. I'm going to move forward now. This is another standing wave, but in reality, the wave is not standing. The wave is moving. Is one wave propagating to the right and another wave propagating to the left. When those two waves combine, it gives you this false impression. It gives you this false impression that the wave is not moving. Okay? That's what you have to keep in mind. Okay? And the same thing happens here with longitudinal waves. Let's take a look here. Why? Let's see this one. Let's 0, 0.5. Let's see. No, that's too much. 0.25. 0, 0.25. Yeah. 0.5. Yeah. 0.75. Yeah, see that? Here's my standing wave. This standing wave here corresponds to the moment in which you have just what you see right in here is analogous to what you see. Let's see. I gotta what you see. 0.5. What you see right in here. The position of equilibrium, the instant of time in which the wave is at the position of equilibrium. That's what is a standing wave here. This longitudinal standing wave is telling us. Okay, that's the case in which there is no, is the instant of time in which there is no disturbance in the pressure of the air. Okay, it's just regular atmospheric pressure. But then as we move along, as we go along, we start to see the nodes, right? The crests, the nodes, and the rarefactions. And here you go. We got there again to the point. Oh, let's see more rarefactions, right? And here you go. More compressions. Okay. That's the phenomenon of interference that we see. So that's what happens within musical instruments that has their ends fixed. Okay, the above model, applies to the string of the guitar, to the string of a guitar with both ends fixed. Okay, both ends fixed. When the bows, which have amplitudes, which have zero amplitude. Okay, if the string has, for instance, if the string has a length L, then we have the following relation. That's what I call the boundary conditions. The resulting wave at x equal to 0 is going to be equal to the resulting wave at x equal to 12, sorry, or 12, which, by the way, is going to be equal to 0, right? Sine of KL is going to be equal to 0. Did you get the idea? Okay, if sine of KL is equal to 0, okay, so what you see right in here, KL can be either 0, but it can also be what else? It can be pi, it can be 2 pi, right? And so on. Should be pi n times pi, where n is equal to 0, 1, 2, 3, like that. Okay? We cannot say much about what happens in between, but at least the extreme, right? At x equal to 0 and x equal to L, the amplitude is going to be 0. That applies for a transverse wave. This applies for a transverse wave. Transverse wave. What time is that? Almost, we have 7 more minutes to go, right? I want to check here in the book what are the sections that we covered. Here you go, principle of linear superposition. We covered that. Let me write it down. Chapter 17. 17.1. Principle of linear superposition. What's the principle of linear superposition? It's just like when two waves collide, you have to sum the separate amplitude of the waves. That the principle of linear superposition is this one that you see right here. The forward propagating wave and the backward propagating wave, okay? That's what it's being applied to. 17.2, constructive and destructive interference. We did that too, constructive and destructive interference. Okay. Constructive interference is when the amplitude of the wave sum up. Destructive interference when the amplitudes of the wave subtract each other. Okay? I'm going to show you an example. And you saw an example, by the way. Let's see, okay, right now you have here a destructive interference. One wave, what the crest of a wave is interfering with the throw of the other wave. They are lined up and they are subtracting from each other. Okay? Standing waves. Okay, so those are the two sections that we were able to cover for this chapter. And you can add those two sections right in here. Okay? We're not going to cover the rest. I'm not going to ask you the remaining of this chapter, okay, in the exam, but you have to know those other two since we worked that out here in the classroom, okay? So this is the whole material of the semester. And also, let me put here reports, right? For labs 1 through 6. No, 1 through 5. We couldn't do 6, unfortunately. Yeah, since we spent so much time with the first lab, right? We end up not being able to cover the other experiments. And we have 3 more minutes to go. I want to thank you all for being here and be patient with me. I know this material is very difficult. Okay, and you might not be grasping everything, but once you start to grasp, you start to have more, a better appreciation for physics, okay? And again, thank you very much for being here with me. We'll meet again on Wednesday? No, on Monday for the exam, right? On Monday for the final exam. And if you need anything, just send me a email message or stay around the next few minutes here. That'll be all. I can stay online for a few minutes if you have any questions, okay? Thank you very much and see you on Monday.
Thank you, Professor.
Welcome. And recording.